Right, so in this exercise, we're going to be finding the greatest common denominator of two numbers or two integers that the user types in. But there's a variety of different ways to solve this, and there's certainly an iterative approach. But I'm going to show you a solution that can be a little counterintuitive, but actually is a really pretty shockingly small amount of code to do this using recursion. So again, you know from the module, from the associated modules here, recursion is just a situation where you're going to call a function a from a, right, from the same function. So function calls itself. Okay, so how does this play into it? You often see recursive definitions in mathematics, and sometimes just in real world scenarios. So there's an algorithm, Euclid's algorithm for computing the greatest common divisor of two positive integers. Um, and it is inherently recursive. The algorithm or the theorem states that if p and q, right, so we've got two positive p and q integers. First off, I want to make sure that positive is defined as greater than 0. All right, so um, for p and q must be integers greater than 0. For any two integers, two positive integers p and q, if p is greater than q, we can say the greatest common denominator between p and q is simply the greatest common denominator of q and p mod q. All right, now a couple things. Notice the reordering, right? It's not, p and q mod, or p mod q and q. It's q and p mod q. That's the recursive step, right? We're going to answer one question, p, the greatest common denominator of p and q, by answering another question. Now, how are we getting closer to the solution? Okay, q is by definition, it's smaller than p, right? And p mod q has to be smaller than q. Anything mod q, right? If we think, what are the possible values that can come out of a mod 10? Well, it's 0 through 9. So both of these numbers, the first number and the second number, are guaranteed to be smaller than the first and second number. Q is guaranteed to be smaller than P because of this rule. And P mod Q is guaranteed to be smaller than Q based on the way the modulus operator works. So we have a recursive call where these values are decrementing. But what we don't have, or what's not completely obvious from this, is the stop condition. And it turns out that the stop condition is sort of, it's not, I didn't completely explain it here. It's sort of embedded in this, the details about these P and Q values. So eventually, as these numbers start decreasing, this second number, Q, is eventually going to decrease down to 0, at which point that is not a positive integer. Q is not a positive integer. All right? And the hidden base case here is that once Q becomes 0, right, how could Q become 0? Well, because we modded P mod Q and we got 0. And that means that P divides equally, or Q divides equally into P. Right, that's a base case because now we've found a value. We found the first value because we're starting from the larger values and working our way down, and we found a value, P, which divides evenly. Okay, so that'll be our base case. When Q is equal to 0, we will automatically say P is the greatest common denominator. Right? P will be passed in as the first parameter. All right, so let's get some numbers from the user. Int input, please enter an integer. Y equals, and actually maybe we should, well, I'll keep it as x and y. Please enter an integer. And we're going to, first off, make sure that x is greater than y. The whole, or the x is, yeah, if x is greater than y. The whole algorithm presupposes that p is greater than q. So if they're not equal to each other, p should be the largest value. So I'm going to swap these if they're in the right order, because the user doesn't really necessarily know our algorithm, right? So we're going to say if x is less than y, swap. And again, we can do t equals x, x equals y, y equals t. Right? That would be a swap. We'd create a temporary variable so we can overwrite it. That's the kind of traditional approach. We can also do xy equals yx, and that'll swap it. That's something unique to Python. It's pretty nice syntax. All right, so finally I'm going to say answer equals GCD of x and y, and print it out. All right, so let's write our function. And I'll use P and Q so it kind of conforms to the problem statement now. So if we've got two positive integers, meaning if P, and remember Q is always less than P, right? By definition, we kind of went through that already, right? P is always less than Q is always less than P. So if Q becomes a non-positive integer, meaning it's less than 1, it's 0, we're done. That's our base case. So if Q is less than 1, we return P. Else, we return the greatest common denominator between, and again moving back here, P and Q is the same as saying Q and P mod Q. And to give you a sense for how this is working, let's just print out P and Q so we can see those values. So we can understand a little bit how it's working. And let's do something like 60 and 45. All right, so we do 60 and 45. Oops, it looks like, oh, I used a plus operator down here instead of a comma, and I need to convert that to a string. Let's do that. Let's rerun that. You can tell the algorithm is working from the incremental printout, but we have 60 and 45. The next, so GCD has been called with 60 and 45. Q is certainly less than or greater than or equal to 1, so we call GCD on Q, the 45's coming in, and P mod Q. So 60 mod 45, 45 goes into 60 once with a remainder of 15. So that's why we got the 15, the 45 and the 15. So now we called that GCD again, and we're going through the same process. Right? Q is being used as the P value, 15. 45 mod 15 is 0. Right? So that's divided evenly, so we know we sort of have found the GCD. But we waited to actually report that because we called GCD on it, we went right back around the loop, but now Q was 0, so we returned P. Right? Once we returned P, we sort of unwound the whole process, and we could add print statements to see that happening as well. And we got our right answer. If we remove some of these printout, the printout at least, you can see just how small this code is, and more importantly, I think it's that when a program or a problem is given to you in a recursive way, it's really nice when the code actually looks a lot like the way it's stated, right? It creates a very intuitive way of understanding the program. There's lots of caveats to recursion, as we've talked about in the modules, but this is a very practical and very good use. This is an algorithm that converges quick enough that we won't need to worry about having too much stack space being used or too many recursive function calls. It's indeed a very, very effective way to get the greatest common denominator.